Okay, imagine you've got something rolling down an incline. Okay, so you get to the bottom of the incline, and I want to know how fast is it moving. Well, this is a problem that we've run into multiple times. We got an incline, it goes down the incline. We want to find out how fast is it moving at the bottom of the incline. You had a problem on the test like this. Okay, so on the test, you simply had, something that was some length L, and I gave you the angle, and we went down the incline. You wanted to find out how fast is it going at the bottom of the incline. And so on the test, it slid down the incline. And so we could do, the conservation of moment, a conservation of energy here. So the initial equals the final. Okay, and so we can put 0 at the bottom down here. It starts at rest. So this is mgh equals 1/2 mv squared. The m's cancel. The h is going to be L sine theta. And so v was square root of 2gl sine theta. Okay, now that is if it slides down the incline. I want to do something different. I want it to roll down the incline. So if it rolls down the incline, so same problem, theta, okay, some length L, now it's like a cylinder or a sphere or something like that, and it rolls down the incline. And so I want to find out how fast is it moving when it reaches the bottom. Okay, so it's basically going to be the same essential sort of thing. Again, we know that h equals L sine theta, just like before. Okay, and so if it goes L sine theta, then we know that the initial equals the final. Okay, again, we can put the final potential at 0, put the initial kinetic at 0. So mgh equals 1/2 mv squared. It looks just like before, except it's also rotating. So it's also rotating. So when it reaches the bottom here, it's rotating. So that means we have the kinetic energy of translation and we have the kinetic energy of rotation. So it's doing both. So we have to include both kinetic energies into the answer here. Okay, so mgh equals 1/2 mv squared plus 1/2 I omega squared. Well, omega squared is v squared over r squared. Okay, and so we know that the h is going to be L sine theta. Okay, so 1/2, or we can even put that in at the end if we wanted to. Okay, so we can solve here for v. So now it's a little more complicated. So v is now going to be the square root of 2mgh divided by m plus I over r squared. Okay, so that's how fast it's moving to the bottom. Well, obviously, I said, it could be a sphere, or it could be a cylinder, or it could be a hoop or a wheel or something, anything round that rolls can be going down. They all have a different I, and if they have a different I, then they're going to have a different velocity. Well, if they have a different velocity at the bottom, they're going to have a different velocity partway through. So whichever one has the biggest velocity would reach the bottom first. So for example, let's say I have two objects up here. We have two objects. Okay, so one object is going to be a sphere, and one object is going to be a cylinder. And I let them go at the same time, and I want to know which one reaches the bottom first. Okay, so if we want to find out which one reaches the bottom first, then we have to figure out I. So I of a sphere is I of a sphere is going to be equal to 2/5 mr squared. Okay, so I of a cylinder is going to be 1/2 mr squared. All right, so that means when we said that the velocity is going to be the square root of 2 mgh divided by I plus m plus I over r squared, okay, so for the sphere, the velocity is going to be the square root of 2 mgh divided by m plus 2/5 mr squared over r squared. So the r squareds cancel. And so we have, in the denominator, we have m plus 2/5 m. That's going to be 7/5 m. Okay, so that means this comes out to be 10/7 mgh. Okay, so for the cylinder, then this is going to be 2 mgh divided by m plus 1/2 m r squared over r squared. The r squareds cancel, and so 1/2 plus 1/2 is 3/2, and so that means this would come out to be 4/3 mgh. Okay. Well, 10/7 is bigger than 4/3. So that means the sphere would go faster. It'd be the first one to reach the bottom. So that would be an example of this. And so if you knew what the angle was and you knew the length, you could plug in here for the h and actually get the answer. Okay, now here's a question. What if I have a cylinder with a different radius? Which one gets to the bottom first? Or if I have a sphere with different radius, which one gets to the bottom first? The bigger one or the smaller one? So what you do is you look over here and you say, well, if I change r, how does that change things? And you look at that and say, there is no r. The r's cancel out. So that means for a sphere or a cylinder, the r doesn't matter. So a small sphere and a big sphere would both reach the bottom at the same time because they'd both be moving the same velocity the entire time at every spot along the way down. Likewise, a small cylinder or a big cylinder. What about if I change the cylinder to a disc? So that'd be like a cylinder that's not very tall. Well, if I change z in this equation, it doesn't change anything because there's no z. And so that means a cylinder or a disc would reach the bottom at the same time as well. Okay, so the only thing that make a difference would be if it was an empty cylinder or if it was a solid cylinder. Okay, because the empty cylinder would have the mass on the outside, a solid cylinder would have mass on the inside. It would make a difference as to the moment of inertia, and so that would change the final answer. So this is an example of how you would do this. So we'll do an example here in just a second. First of all, I'm going to show you a video actually showing this sort of thing and happening, and then we'll do an example.